So it says, consider a car of mass m moving with an initial speed v0 on a straight, flat road. At time t equals 0, the driver fully applies the brakes to avoid colliding with debris in the front of the in the road in front of the car. The car's wheels lock, causing the car to slide on the roadway until the car stops before running over the debris. The distance that the car slides is d. The coefficient of kinetic friction between the car's tires and the roadway is a constant value, mu sub k there. So first thing is free body diagram. Clearly, as always on this planet, we're going to have gravity. So I'm just going to go 1, 2, 3, 4, 5 down. I'm going to label that the force of gravity. And then we will have to have a normal force up. So 1, 2, 3, 4, 5. The normal force must match the force of gravity because we are not accelerating in the y direction. And then the car is going this way and it's sliding, so friction will oppose it back the other way. So 1, 2, 3, and again, we don't know the relative lengths, but we just know that these two have to match each other in lengths there. So next part says, the stopping distance d depends on the value of v sub 0 and mu sub k. Does the value of d increase or decrease with the initial speed v0? Give a physical explanation as to why this is the case. Well, I think any person you would ask, whether they had physics or not, would realize that the faster you were going, that the distance it took you to stop would increase. Why is that? Well, talk about things that are the same too, and you might want to mention an equation. So you might want to say like, well, every single time our final velocity is going to be 0. Every single time our acceleration is going to be the same because acceleration is going to be dependent upon friction. So, and the acceleration, by the way, is proportional to the force, remember, and the force is proportional to the amount of friction there. Where did I get those two statements? That's just A equals F over M, and force of friction equals mu times normal force. So that's how I can say those two things. So anyway, since the acceleration is the same and the final velocity is always the same, if you're going to look for the distance, it's actually what we've been calling the fifth equation, if you look at that. So this part will drop out to 0, and so the distance you go here will increase as the initial velocity goes up. This one here says, does the value of d decrease or increase with the coefficient of friction of mu sub k? Well, so as our coefficient of friction goes up, I think, again, it's a very intuitive guess that the distance you slide will go down. And that goes back to sort of what we were saying here. If your friction is proportional to the coefficient, so a bigger coefficient means more friction, and acceleration is proportional to your friction. So in this case, rather than acceleration being constant, friction is going to go up, acceleration is going to go up, so you will come to a stop more quickly than before. They want us to write two different Newton's second law equations, one for the vertical and one for the horizontal. So let's start those. So they've started us on the vertical one, and they want you to say an explanation too. And I'm just going to, or write it, I'm going to just say it. That the sum of the forces in the y direction is the mass times the acceleration in the y direction. I'm going to go ahead and add here that we know there is no acceleration in the y direction. So we can write this, that the sum of the forces in the y direction must equal 0. Now, let's talk about what are the forces in the y direction. We've got the normal force up minus the force of gravity down. That's got to equal 0. And so we can make the next statement, which is pretty obvious. We did it from the very beginning, that the normal force must be equal to the force of gravity. What about in the x direction there? So in the x direction, let's write it again. The sum of the forces in the x direction is equal to the mass times the acceleration in the x direction. What are our forces in the x direction? We've got, well, only one thing. We've got the force of friction backwards the other way. You can put it as a negative if you went there, and that is going to be equal to mass times the acceleration in the x direction. Now substitute in for what force of friction is equal to. The force of friction is always equal to mu times the normal force, and that's going to equal mass times the acceleration there. Then let's plug in for normal force from what we just said up here. We said that normal force is equal to the force of gravity. So, and actually here, you know what I could say too, that the force of gravity is m times g. Because up here they want it in terms of, if you look here, mass times mass or gravity or acceleration or mu. Those are what can be in your answers there. So anyway, I'm going to substitute in for that. I'm going to start writing up here that substitute in for the normal force is going to be mass times gravity. And that is going to equal mass times acceleration. Look at this. This is the first time we've seen in one of these cases something that happens a lot in physics. You have a mass on this side of the equation and you have a mass on this side of the equation. So the masses cancel out there. So it turns out that the mass of the car doesn't make any difference in terms of the acceleration. How can that be? Well, let's go ahead and sort of solve for this. So the acceleration in the x direction is negative mu times g. There's two counteracting effects. So the more mass an object has, the more it wants to stay in motion. So that would tend to, it seems like, to make the acceleration less. But the more mass it has, the more weight it has, the more normal force it has, the more friction it has. And those two effects basically cancel each other out there. So next part here, it says, write an equation for d in terms of v0, g, and mu sub k. We started to kind of do this on the other page. The fifth equation is what will get us there. So the final velocity is equal to the initial velocity plus 2 times the acceleration times mu sub k. This, remember, is 0, the final velocity, because it comes to a stop. Like that. So then I will substitute in for, or I will subtract this v0 to the other side. So negative v0 squared. I'm going to go ahead and divide by, whoops, sorry. What am I doing here? I made a mistake. I don't know why I wrote mu sub k. This is delta x. This is delta x. And so that is effectively our d there. So minus this to the other side, negative v0 squared, divide it by the 2a, and that is equal to delta x, which is our d. So we can put that in there. And then one last thing is I'm going to substitute in for this a from what I wrote on the previous page. So negative v0 squared over, remember I said a is equal to mu times g. So negative mu times g. And that is equal to our distance there. So last part is, it says, explain how your equation from part D, right up here, supports your reasoning about the relationships among d, v0, and mu sub k that we outlined in part B. Well, in part B, we said more initial velocity, more distance. Well, we can see that here. In fact, it's a square, so if we double our initial velocity, because it gets squared, we'll have 4 times the distance that we go. And then we said more coefficient of friction, less distance. And we can see that because it's down in the denominator of this equation. So if we doubled our coefficient of kinetic friction, you can see we'd have 1/2 the distance of before.